Okay, so this is the first of 3 videos I'm going to make on electrolysis. We'll start by just discussing what electrolysis actually is. So you can see I've split the word in half to electro and lysis. So the electro implies that we're going to use electricity, and lysis just means split. So the word electrolysis means the use of electricity to split something up. In terms of what we are splitting up, we are going to be splitting up something called an electrolyte. And when we're using electricity, instead of using alternating current AC, we're using direct current DC. So what exactly is an electrolyte? Well, an electrolyte is an ionic compound that's either liquid, so you've melted the ionic solid, or aqueous, you've dissolved the ionic solid in water. And the reason the ionic compound must be liquid or aqueous is because it must be able to conduct electricity. And for ionic compounds, they only conduct when their ions are mobile, and their ions are only mobile in liquid and aqueous phase. So if we look at some examples maybe of an electrolyte, if I had sodium chloride, that's ionic because I've got a metal and a non-metal, and I've made it molten, so I've taken that solid and I've melted it. That means it can conduct electricity because the ions are freely moving, and then I can split up this electrolyte into the 2 elements it's made of, sodium and chlorine. Another example, if I have iron bromide, again, I make it a liquid so it conducts electricity, and when I split it up using electricity, I get the 2 elements, iron and bromine. Okay, at this point, I want you to pause, and I want you to do the first 4 questions from your quiz on page 2 of your homework booklet. Right, so please do the questions yourself instead of just copying my answers. It's much more effective that way. Hopefully you have got them done. So when I ask what is electrolysis, it's just a process where electrolytes are split using electricity. What type of current is used? It's direct current, so you can say DC. What exactly is an electrolyte? An electrolyte is an ionic compound that conducts electricity, therefore it's going to be liquid or molten. So these 2 are just taken straight from the specification. There are probably other ways you can phrase this that it's acceptable on a mark scheme, but I've just written what they've got in the spec. And then the final one, explain why solid sodium chloride is not an electrolyte. How can you make it one? Well, if it's solid, the ions are not free to move. So don't just say it cannot conduct electricity. Tell me why. The ions are not free to move in a solid, so it cannot conduct electricity, and therefore it cannot be split using electrolysis. To make it into an electrolyte, all I need to do is melt it or dissolve it. Once I do that, the ions can move freely, it can conduct electricity, and it can be split up. So you're often asked to draw the apparatus that will be needed for electrolysis. Because we're using electricity, we need some sort of power supply. So this is my rough attempt at drawing a battery. Unlike in physics, this is a totally acceptable representation of a battery. You could even just draw a rectangle and write power pack or power supply, or draw a rectangle and write battery. You don't need to be able to draw it as you do in physics in an electrical circuit diagram. So I've got my battery, and I've got this beaker here to contain my electrolyte, my molten ionic compound. So I need the electricity to get from the battery into the ionic compound. For that, I can't just drop the battery into the ionic compound. Instead, I'm going to attach the positive end of the battery to a substance called an electrode. I'm going to attach the negative end of the battery to a substance called an electrode. I'm going to put those electrodes into my ionic compound. Remember, your ionic compound is always going to be in liquid form. So let's just say I have sodium chloride as a liquid. That's my electrolyte. And then these are called electrodes. So if we look at the electrodes in more detail, okay, they can ask you what would be suitable as an electrode. 3 criteria an electrode must fill. The most obvious one is electrodes have to be able to conduct electricity. You need the electricity to get from the battery into your ionic compound. They must be able to conduct. Your second thing is you want your electrode to be inert. Inert just means unreactive. You don't want the electrode to be able to react with the ions in the electrolyte, so you want them to be unreactive. And then the last thing is you need them to have a high melting point. So if we look here, sodium chloride, I need to keep that in liquid form. To do that, I'm going to need to use really high temperatures. Remember, ionic compounds have high melting points because of the strong electrostatic forces of attraction between oppositely charged ions. So if I want to melt sodium chloride, chloride and I want to keep it as a liquid, I need to use high temperatures. I don't want my electrode to melt into the electrolyte, so my electrode must also have a high melting point too. Can you now please go and do questions 5 and 6 from your quiz? Okay, so hopefully you've actually done these. The first one, draw the apparatus used to electrolyze molten sodium chloride. So these are really common 2-mark questions. So again, I've just written this kind of like crude representation of a battery. That's absolutely fine. I've got my beaker. I've shown that my electrolyte is in liquid form and that my electrodes are submerged in my electrolyte. If you drew something like this, where the electrodes were floating above the electrolyte, you obviously won't get the marks. The electricity cannot jump across this empty space and enter the electrolyte, so the electrodes have got to be in the electrolyte. They don't have to be fully submerged, but they have to at least be in the electrolyte. The next one, why is graphite a suitable material for an electrode? So just remember the 3 criteria I mentioned, okay? Graphite can conduct electricity. We learned that it's got delocalized electrons. Graphite is inert, okay? It's not reactive. Graphite is just like the stuff that you've got in your pencil. It's not reactive, and it does have a very high melting point because of all of those strong covalent bonds that you would have to overcome. All right, so the next bit is maybe a little bit trickier. You're going to be asked to describe what happens during electrolysis. Often you're asked to describe what happens at the cathode or what happens at the anode, so it's important you can identify which one is which. So down the left here, I've just written panic. Positive is the anode, so the positive terminal of the battery here I'm going to label as anode, and negative is cathode. The negative side I'm going to label as the cathode. And often you're asked to describe what happens at the anode, describe what happens at the cathode. Now before I go any further, I just want to make something clear. We said there was 2 different ways to make an ionic solid conduct electricity. I can melt it and then it's molten, or I can dissolve it in water and then it's aqueous. The method that you use affects this part. Molten is easier. I'm just going to do molten in this video. And then aqueous, which is when hydrogen gets introduced, I'm going to deal with that totally separately in another video. So we're just going to deal with molten electrolytes, describing what happens at the anode and what happens at the cathode. Right, I'm going to take an example of an electrolyte then. I'm going to take, let's say we do calcium chloride, okay? That's an ionic compound. It's got a metal and a non-metal, and I'm going to make it molten so that it conducts electricity, okay? Because it's an ionic compound, it is made of ions. It's got the calcium ion. Calcium's in group 2, so it's got a 2+ charge, and it's got the chlorine ion. Chlorine is in group 7, so it's got a -1 charge. When you're working at the charges and ions, it doesn't matter what the formula is, you just look at the groups. Group 2 is +2, group 7 is -1. It doesn't matter what they're bonded to. So these are the ions that I've got present in my electrolyte. And step 1 of electrolysis is just going to be to separate those ions. So the first thing I'm going to do is I will separate the ions. And this bit is quite straightforward. We know that opposites attract. As soon as you turn on that battery, this whole electrode is going to become negatively charged, and the positive calcium ions are going to be attracted to this cathode. When I turn on the battery, this electrode is going to become positively charged, and my negative chlorines are going to be attracted to that anode. So step 1, separate the ions, nice and straightforward. Now step 2 tends to be what students overlook. This is really important because it's where most of your marks come from. You are going to discharge the ions, okay? And what I mean by that is you're starting with ions at the moment, all right? So you're starting with something charged, but at the end of this process, you need to have something neutral, something with no charge. So you're starting with ions, they have a charge, and you're converting them back into just the neutral elements. And this is the part of the description that students tend to either forget about and not mention at all, or they just struggle. So we're going to come down here and I'm going to split my page in two. We're going to describe what happens at the cathode, then we're going to describe what happens at the anode. And when we're doing our descriptions, to make sure we're picking up all the marks, I'm going to give you 4 kind of success criteria. First thing you're going to do is describe the movement of the ions, which ion moves where. Then you're going to write me a half equation because it just mops up all of your marks. Then you're going to tell me if your half equation represents oxidation or reduction, and then ideally, in some cases, you're also going to tell me what you're able to see. All right, so at the cathode, which was our negative electrode, we said the positive metal ions were attracted to the negative cathode. All right, so I'm going to write here Ca2 plus ions migrate or move to the cathode. Okay, opposites attract. And then I'm going to write a half equation. So we said here, you need to start with something charged and turn it into something neutral. So the thing that I'm starting with is the ion, the calcium ion, and I need to turn that into something neutral. So I just write calcium as I normally would if it's an element. When I write calcium as an element, it's just Ca. Calcium is a metal, so it's going to be solid. So how am I going to go from this, Ca2 plus, to this, Ca with no charge at all? How am I going to discharge my ion? Well, if we look at calcium, it's got a 2 plus charge, which means it has lost 2 electrons. If you give it those 2 electrons back again, so give it back the 2 electrons that it lost, then it won't have a charge anymore. So that's my half equation. Is this oxidation or reduction? Ca2 plus is gaining 2 electrons, so I can say this is reduction. What am I going to see? Okay, calcium is a metal, metals are solid. What am I going to see? I'm going to see a metal being deposited onto that cathode. So if I came back up here, as soon as all of those ions are turned back into calcium atoms, you're going to see the calcium build up on the cathode. You're going to see the silver metal be deposited onto your graphite electrode. What happens at the anode? Well, in terms of movement, the anode is positive, so the negative ions are going to be attracted there. So I'm going to write Cl minus. They are going to migrate to the anode. The half equation, all right? So Cl minus, I need to take something charged and turn it into something neutral. So chlorine, when it's an ion, is Cl minus. Chlorine, when it's an element, you have to remember it's Cl2. So we recently did writing and balancing equations, okay? We learned that chlorine is diatomic, so you're on the right-hand side, you're writing the elements as they would appear if they're just normal elements. So I need to make that Cl2. Now, at the moment this isn't balanced, I've got 2 chlorines on the right, I need 2 chlorines on the left. I cannot use a little 2 here. That implies that the negative chloride ions are forming a bond with each other. They're not. They're negative. They repel each other. By putting the big 2 in front, it tells me I've got 2 separate chloride ions. Now, in order to discharge them, remember they're negative because they've gained an electron. If they lose that electron, they won't be negative anymore. So you're taking away the electron that it had gained. Now, there are 2 separate chloride ions. They each need to lose 1 electron. So in total, I'm removing 2 electrons. And when you do that, the 2 chlorine atoms can form Cl2. So that's your half equation. Because I'm losing electrons in this case, I can say that this is oxidation. And in terms of what we'll see, calcium is a metal, so we said it's solid. Chlorine is a gas, and if you're forming a gas, you are going to see bubbles, all right? Really important you try these ones for yourself, okay? Can you do 7, 8, 9, and 10? Press pause, have a go, and then press play when you're ready for the answers. All right, so question 7, what happens at the cathode when molten sodium chloride? So remember, panic, negative is cathode. If it's negative, the positive sodium ion is going to move there. So first point is movement. Sodium ions migrate to cathode. When they get there, what happens? They are discharged. So your positive sodium gains back the electron it lost to become sodium metal again. Because it's gaining an electron, this is reduction. Because I'm forming a solid, I will see that metal be deposited onto the cathode. So you're going to see a silver metal be deposited onto the cathode. Question number 8, what occurs at the anode? So the chloride ion is going to go to the anode. When it gets there, it's going to be oxidized. So it's the same half equation I wrote a moment ago. Because chlorine's a gas, you're going to see bubbles. The next one, when you've got molten magnesium bromide, so in this case magnesium is the positive ion, it's going to go to the negative cathode. Because it's in group 2, it's got a 2+ charge, so it migrates to the cathode. When it gets there, the magnesium had lost 2 electrons, you give it those 2 electrons back, now it is a neutral magnesium atom again. So this again is an example of reduction. Because magnesium is solid, you see that metal be deposited. And the last one, the anode, the bromine, the Br- are going to go to the anode. When they get there, they're going to be oxidized. The half equation is exactly the same as it was for chlorine, because bromine, like chlorine, is diatomic. Bromine is a liquid. I actually don't know if you'd see the orange liquid or not. I don't know if you'd actually see it, but bromine is a liquid, and in solution it's an orange color, so that's the only reasonable thing that you can say if you were asked for an observation. 2 things to note, okay? When you're discussing the cathode, you'll see that there's similarities. It's always the positive ion going to the cathode, and the positive ions are always reduced, so you can learn reduction occurs at the cathode. With the anode, it's always the negative ions going to the anode, and those negative ions are going to be oxidized. So again, you can learn those things off by heart, but it really helps to understand them. Please make sure you practice writing your half equations. They just mop up all of the marks, and the mark scheme allows you even to make small mistakes in your half equations, and it still gives you all the marks. So the standard here is quite low. If you can write those half equations, you'll do really, really well in electrolysis.